So we're going to talk about what's called mathematical induction, which is a form of proving sequences and series. So we're going to be looking at sequences and series, and we're going to try to prove some kind of summation formulas for these guys. Now, this right here, 1, 3, 5, 7, that's a certain type of sequence. We've seen one like that before, right? And we can actually do a fair amount with that, right? What are the things that we've done with that so far? For example, we've done a sub n, right? Could we do that?
We can find the partial sum.
Okay, we can find the partial sum, right? We can find, can't really find the infinite sum on this one because, that's right, because the ratio is bigger than 1, right? And it's not geometric either. So the infinite sum for this would continue to grow. So there is no specific value for that one, okay? But I could write the a sub n. Go ahead and write the a sub n formula for that one. Let me make sure that they're here. Caleb, Tyler, and Todd. Yeah, we're good. We're good, thanks. Yeah. Go ahead and write the a sub n sum for that. Or I'm sorry, just a sub n equation for that. So what did you guys get? 2n minus 1. We okay with that? Now, what this does, a sub n, this generates each individual term in that sequence. So if I want the third term in that sequence, I would find, for example, a sub 3. I would just plug a 3 in. So it would be 2 times 3 minus 1. So 6 minus 1 is 5. So that's where I get the 5 right here. Okay? So this formula right here, 2n minus 1, this generates individual terms for me. Okay? Everybody okay with that? We've done that before. Nothing crazy, right?
Yeah.
Okay. Now let's say I put a little sigma in front of there. In front of that, 2n minus 1. And I go n equals 1, let's say to 4. Find the sum of the, they would call this a partial sum. I want to find the sum of the first 4 terms here, right? I'm going from 1 to 4, so I have 4 terms here. So if I were to evaluate this, right, first off it's arithmetic, so I could use the formula, or it's summation, so I could, or it's only 4 terms, so I can just add it, right? If I plug in a 1, it would be 1, right? 1 in there is 1, plus, if I plug in a 2, well, I got the sequence right there, 3, and then plus 5, and then plus 7. Is everybody okay with that?
Yeah.
Okay. Jackpot. Everybody's happy, right? Nothing earth-shattering going on right now? We already learned this. Yes, I'm happy. What happens if I add all those numbers together? What do I get? 16. All right, that sounds pretty good. Now, what if I went the number before that? What if I did the sum for this guy? N goes from 1 to, let's say I just went to 3 of that guy. So that would be 1 plus 3 plus 5, right? Which would equal 9 if I were to add those together. Are we okay with that? Okay, let's do the first 2 terms. N equals 1 to 2, of 2n minus 1. Well, that'll be 1 plus 3, which equals 4. Well, they're square numbers. Interesting. Okay, so this summation right here, this summation I could write as n squared. Okay, so the sum for the formula for this guy is going to equal n squared. So if I want to find the sum for the first 4 terms, I could just plug a 4 into this formula right here. A 4 into that formula right there. 4 squared is 16. The sum of my first 4 terms right there is n squared. Okay? If I want to find the sum of the first, let's say 20 terms, right? 20 terms would be pretty big for me to draw. It is arithmetic, so I could use the arithmetic sequence. Or the first 20 terms, I could just put the 20 in here, go 20 squared, and get 400. The sum of the first 20 terms of this sequence right here would be 400. Okay? Does that make sense? Kind of where we're going there? A little bit? So what I'm saying is this. If I go to the sum of 2n minus 1, right? The sum of that particular sequence right here. This equals n squared. Okay? Well, because this is different for every different sequence, right? If I did 2n plus 1, this would no longer be n squared. You could probably figure out what it is, but it would no longer be n squared. Okay? Now, this equals the sum of the n formulas right there. Okay, now we just did it for 1 right here. What we want to do today is we want to try to prove that this is actually true. Okay? Now, to prove this, we do this by what's called mathematical induction. And the proof for it is this. The first thing you do, it's a 3-step process for proving with mathematical induction. The first thing is, check to make sure it works for the first term. Very simple step to do. Check to see if it works for the first term. If it works for the first term, what they want to do is they want to check to see if it works for all the terms after it. Okay? The way I like to think about this is kind of a domino effect. Okay? If I can prove that if I have a bunch of dominoes in a row, 100 dominoes, right? And if I can prove that any domino I pick in there, if I tip it over, will continue all the way through. If I prove that goes down all the way, then I've proved that will always work. So that's, in essence, what we're going to be doing today. So if I want to take a look at the sum formula, let's say I did this. If I take the sum of my n formula, that's 1 plus 3 plus 5 plus dot, 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 plus 2n minus 1, that's going to equal n squared. Now this is pretty much what they're going to give you to start with. They're going to give you this. they're going to say, all right, the sum formula is the sum of all these terms right here, and the sum, all of those added together equals n squared. So they're essentially saying that the sum of the first n terms is n squared. That's going to be different for each individual sequence that they give you, okay? What I want to do is I want to prove that this is true, okay? And the nice part is if you're proving it's true, it's already true. It's kind of like the verifying from the last chapter. It's going to be true. There's none that are not going to be true, okay? So the first thing I want to do is I want to check to make sure this works, this formula works for the first one, okay? So all right, so let me just write this down here. Step 1, okay? We want to show it's true for 1. Show true for n equals 1. That's the first step we're going to do. The second step is super lame. Very, 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 very lame. Because we don't know that this is true yet, technically, this is kind of a technical step here. It's kind of a lame step. You want to assume true for, I know I hate that, n equals k. Okay, so we're going to assume it's true for n equals k. Basically, some other dummy variable. Okay, we have some other variable that's in there. I want to try to prove it on that variable. If it works for any variable that I pick, it's got to work for the original ones too. Okay, step 3 is the tough part. Step 3 is the tough part. You want to prove that it's true for n equals k plus 1. And that's the domino effect there. If you can assume it's true for the first one, and then you can somehow prove that the next line, the next number in that sequence, k plus 1 term, if you can prove that that part's true, then we're going to assume that that sum is going to be true for anything that I give you. Okay? So this is the 3-step process that we're going to go through for all mathematical induction. It's always the same thing. Okay? Now, for step 3, I'm going to put a little asterisk down here for step 3. This is essentially what we're proving. We're going to prove the sum of the k terms. If I add the next term into that, a sub k plus 1, that should equal the sum of the k plus 1 terms. I know that part's kind of a mouthful, and I'll show you how this is going to work in a second. But I'm taking the sum equation, I'm adding a term to it, and I want to show that that equals the sum equation with that next term plugged into it. That's essentially what we're looking at here. Okay? So the sum formula plus the next term, and then we're going to make sure that that equals the sum with that next term already plugged into it.
What's k?
Okay? K is going to be some constant, some value that we don't really care about. That's what's kind of weird about that step. Is it's kind of a dumb step, and I'll show you. I'm going to go through the steps of the process right now. Right now, I'm just explaining kind of where we're going to head. Okay. All right. So everybody have those written down, so you can erase those. Okay. So step 1. What does step 1 say? Show it's true for n equals 1. So that means I want the sum when n equals 1, and that better equal 1 plus. Well, I only want one term, right? Equals 1 squared if I plug a 1 into n right there. So I get 1 equals 1. Is that true? True. Done. Got it. Okay, so the first step is done. That was easy. Right? The third step is the hard step. The second step said assume it's true for n equals k. Well, that means you just assume it's true, so we're going to go s sub k equals 1 plus 3 plus 5 dot 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 plus 2k minus 1 equals k squared. Done.
So k is just essentially n.
You're essentially plugging in k for n. They don't want you to use n because n is what you're trying to prove, so we have to swap that out and say any other letter is going to work here. If I can prove it for a different letter, it's going to work for the original. It's a bit of a technicality. The second step is kind of lame. I'm not going to lie to you. It's kind of the dumb one out of all this, okay? The third step is the hardest step to do, okay? The hardest step. This is where the actual math comes into play, okay? We want to take the sum. I'm just going to rewrite it right here. This is step 3. I want to take the sum of the k terms, which is all of these terms mixed in here, and I want to add one more term to it. I want to add a sub k plus 1, and that's got to equal s sub k plus 1. That's got to equal the sum of all of those terms mixed together. Okay, so essentially this is what we're going to do. We're going to take the sum formula with a k plugged into it, right? So what's the sum formula with a k plugged into it? Let me just briefly write one more time. This right here is s sub k, right here, and this right here is a sub k. Okay, this generates a term for me. This generates the sum for me. Okay, so those are the two different ones you're going to use. These two guys right here.
So s of k is k squared.
So s of k is k squared. So we're going to take k squared plus, we want to take a sub k plus 1, which means I want the k plus 1 term. I'm going to plug k plus 1 in for that k right there, into the a sub n formula. Okay, so I'm going to go to k plus 1 minus 1. I plugged in a k plus 1 right in here. And then I want to make that equal the sum formula with k plus 1 plugged into it. Now the sum formula is this guy, and I'm going to plug in a k plus 1 into this. So it's going to be k plus 1 squared. Okay, I'm literally just putting k plus 1 in for both of those guys. Okay, and I'm going to write it in a different way here in a second, just so maybe it's a little clearer for you guys to see. But now what I want to do is I want to show that this is true. I want to prove that this is true, that these are the same. So we just have to do a little bit of algebra now, okay? We just have to algebraically simplify this and show that it's true, okay? So if I simplify this a little bit, let's simplify this and see what we get. We get k squared, plus if I distribute my 2 in there, that's going to give me a 2k plus 2 minus 1. Now I can simplify that, add like terms together. K squared plus 2k plus 1, which we can factor.
So what the k squared with sk is?
Yeah.
I'm kind of confused why you put 2 and then parentheses k plus 1.
Okay, right here. Here's my a sub n formula, right? This generates a term for me, right? And that's a sub k plus 1. So what I did is I plugged this k plus 1 in for this k right here. I replaced this, I replaced this with that. So that's why it's the 2k and then minus 1. This is essentially my formula right there. Okay? So I'm just replacing both of these k's really with a k plus 1 here and here. That's all I did with that. And then I left the sum formula alone right there. So, yeah.
Are we always going to do it that way?
Well, this is always the same way to do this on every single problem. They're all going to be the same. Okay, so once you get the process down and kind of understand what the heck we're even doing, it won't be too bad from here. Okay, now k plus 1 times k plus 1 is k plus 1 squared, which equals what I wanted it to equal, k plus 1 squared. And so we say check mark, done. That's where that math is going to come in, the algebra. Okay. Now, since that's all good, basically this right here was the domino effect. I proved that any term I pick, I can show that if I add another term to it, it's going to be true. I've proved it mathematically here. So that means that this whole domino series is going to work. So you can say, therefore, S sub n equals 1 plus 3 plus 5 plus plus 2n minus 1 equals n squared. Yay, done. Smiley face. Okay? Now, I want to write it in just a slightly different way, just to maybe help you see this part again. Okay? This is the hard part for this entire stuff. It's S of k plus the next term equals the sum with the next term plugged into it. Okay? Let me just show it to you in this way. Okay? If I'm going to erase some of this stuff, is that okay? If I erase some of it? Good. Great. So let's say I took the sum. Where's that? Okay, let's say I took the sum of my k terms, and it was 1, and then equals k squared. K is going to be just a 1 on this one, the sum of the first terms, right? And if I add the next term to it, I'm basically showing that if I go plus 3 and plus 3, is that true? That's essentially what I've done, is I've added the same term onto both sides, okay? I've added whatever the next term in the sequence is onto both sides. Now this would be k plus 1 for that formula, okay? So I'm adding whatever that next term is, okay? If you thought about it this way, what would be the next term after 2k minus 1? I know it's kind of weird. What's the term after 5? 7, 9, right? What's after 2k minus 1? Well, it would be a k plus 1 plugged in there. So it would be 2k plus 1 minus 1. That's the next term after this one. That's another plus 1 tacked on the inside. The next one would be 2k plus 2 minus 1. Next one would be 2k plus 3, right? So that's the next term in that sequence. So that's all we're really doing is adding one more term to this and saying that that works for the summation formula as well. Okay?
How'd you get that it's 2k
I'm just saying, if I were to plug in a number, like let's say I did a sum like here, and I said n equals 1 of 2n minus 1, right? I started by plugging in a 1, right? The next number I plug in is a 2, and then a 3. So I'm always adding 1 every time I do it. So that's essentially what I'm doing is I'm taking k, and I'm just putting a plus 1 next to it. Okay? All right, let's do, we have a couple more of these to do, a couple more challenging ones. I know the second step's kind of silly, but we can't use ends on this, unfortunately. So, let me do. How about that one? That one was semi-hard. Yeah, we're going to do it to appease the math guys.
What are the math guys' names?
Gumkey and. Well, that's pretty much it. There's only one.
Well, Mrs.
She's an English god. Got it. Yeah, thanks. I got it. Okay, now the formulas get a little trickier. They're not always going to be n squared, right? This one's 1, 2, 3, 4. That's the sequence. It's arithmetic, right? We can tell that. We can write the a sub n term for that, although we kind of already have it right there. And that's what this part is right here, okay? Some people like, right at the beginning, they like to write this. They like to say that this is my a sub n part right here, and this is my s sub n part right here. It helps them line up that third step a little bit better, okay? The third step is going to be the toughest step for all of you guys, okay? But this right here is the a sub n. This gives me any term in the sequence. This gives me the sum of all those terms in the sequence. So that's the difference between these two guys right here, okay? So let's go ahead and do our first couple steps. I know they're kind of silly, but the step one is to check to make sure that the sum works for the first term, right? So that means I want to plug in. The only first term in this sequence is 1, and I want to make sure that equals a 1 plugged into my summation formula. So it's going to be 1 plus 2 divided by 2. Did I write this one down?
Doesn't seem like it matches up.
Oh, I wrote it down wrong. Sorry, guys. My bad. It should be a plus 1. Sorry, my bad. And n plus 1 over. I was just saying, the first one didn't even work. We'd have been done. Yeah, no solution, which is not true. That's all we'd have to do. So we check to make sure it's good for the first term. So we take our sequence that's correctly written down, and we find the first term, which is 1, right? And then this one, we've got n plus 1 over 2. So I want to plug a 1 into the summation formula, which is the sum of the first terms. Okay, and so the sum of the first term, right? So we have 1 times 1 plus 1 over 2. So if we simplify that, that's 1 multiplied by 2 over 2, which equals 1. So 1 equals 1, we're good. First step is good. Usually everybody gets that step. That's not too bad. Usually everybody gets the second step. Second step is assume it's true for k, for n equals k. So we're going to do the sum of the k terms, which is literally you copy that line again and put k's in frames. That's literally all you're doing there. So it's 1 plus 2 plus 3 plus dot 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 plus k equals k plus 1 over 2. Done. Yes, if you're going to get a third of a credit for these problems, you might as well do both of the easy ones, right? Yes, that's right. You're welcome.
You get a third of
Wouldn't it be 2/3?
Oh yeah, he was saying he wanted to just skip the second one.
Oh.
So. All right, now the third step, the hardest part about this whole thing, and it's the same formula that you're plugging into here, is taking the sum of the k terms, adding a term to it, adding the next term of the sequence, which is k plus 1, and then that should equal the sum of the k plus 1 terms. So k plus 1 terms. You're going to use this for every single third step, no matter what. Okay, we're taking the sum of the first 10 terms, adding another term, and saying that equals the sum of the 11th term. Does that make sense to anybody by chance? Should I write that number down? What if k were 10? Let me do an example of numbers. What if k were 10? This would be the sum of the first 10 terms plus a sub 10 plus 1. So the 11th term equals the sum of the first 11 terms. Does that make more sense? So if I take the sum of the first 10 numbers and I add the next number in the sequence, that better equal the sum formula with 11 plugged in. Okay? So that's what this guy is trying to say, but this is with just actual numbers. Okay? And that works for any k. That's the idea. Is any number I plug in for k right there, that should hold true. I should be able to prove that, right? So if I pick 100, if I find the sum of the first 100 terms, and I add a sub 101, right, that should equal s sub 101. Should equal the formula with 101 plugged into it if I add that 101th term. 101st term. 101. That'd be cute. Okay, so let's do that guy right there. So we're going to take the sum formula. Now, once again, people like to write this down. This is the sum formula. This is the term formula. This formula gives you the term in the sequence. This one gives you the sum in the sequence. So I want the sum with k plugged into it. Well, that's just this guy. You just copy that. So it's going to be k plus 1 over 2, plus, now I want the a formula, that's the term formula, with k plus 1 plugged into it. So I want to plug it into this guy right here. So I want to replace k plus 1 in for k right here. So that's going to be k plus 1. And then now that's going to equal...
Wait, I don't get why you make k plus 1 a substitute.
This right here is my a sub n formula, right? So I plugged this right here in for that. I replaced this with that. I swapped these boxes out. Okay, so that is my new box, whatever goes there. If I had a 3 in front of there, it would be a 3 parentheses k plus 1. Okay? Okay? right, now I want to plug in a k plus 1 in for both of these k's right here. Okay, so basically for this k right here and this k right here, I'm replacing both of those k's with a k plus 1. Okay, so these k plus 1s go in for both of those guys. So it's going to be k plus 1 plus 1 over 2. Okay, I overkilled it a little bit on that one just to so you maybe see it a little bit better. Okay, so I replaced both of these k's with k plus 1 and k plus 1. Well, now we just need to show that these are true. We need to show that these are equal to each other. Somehow we have to show that they're the same. Okay, so we're just going to manipulate both sides algebraically, however we have to. Okay, so let's go ahead and do some manipulations. First off, I can simplify the right to k plus 1, k plus 2 over 2. That's the right side. Everybody okay with that? Now I want to make this side look like this side if I can. So common denominator is a good idea. So I'm going to go a 2 on the bottom here and a 2 on the top here. And I'm going to show you a fancy way. You're going to have to probably factor on these no matter what. Some people are going to FOIL all that stuff out and add the like terms together and then factor. Okay, I'm going to save you a small step. Keep it in the broken down form, and then we're going to factor it by a different strategy here. Okay, so let me give you that different strategy.
You're awesome.
Yeah, no problem. So the strategy I would do, so we got a common denominator, right? Great idea by Mike. So now we're going to go k plus 1, and then plus 2k plus 1, all divided by 2. Right? We're trying to prove that those two guys are equal to each other. So I did a common denominator. Now if you'll notice, look at that. Didn't we factor stuff that kind of looked like that? Factor by grouping. Remember that from a while ago, right? Factor this by grouping. So if I were to finish factoring this, Todd, I would factor by grouping. So I would take out a k plus 1. It's not your fault, Todd. Blame them. So I'm going to take out a k plus 1. And if I factor that out, I'm left over. If I take a k plus 1 out of this guy, I'm left with k plus 2. So k plus 2.
Well, they look the same.
Because they are. Done. Jackpot. Happy. I did a common factor of k plus 1 and k plus 1. I pulled that out to the front here and here. And then I'm left over with k and then plus 2. That was this k plus 2 right here. Okay.
Do we ever use numbers?
Yeah, on the very first step, you plug in a 1.
What do you mean, like?
That's a real number.
Okay. What is this K for K's and M's?
K is a random number. K is any number I want it to be. K is N. If I prove it for K, I'm variable. At what point you could plug and chuck stuff in. You could see if it works for the first one, the second one, the third one. That you could do as many as you want, and be happy. But this is a way to prove it in general. Prove it so that I don't have to test a bunch of them. I can just test one. That number happens to be K. See if it works. Okay. Yep. What's that? It's exactly like verifying. That's all we're doing. Because they're telling you it's true. We're just trying to prove that it's true.
So, I'll rephrase my question. We're always going to be working with a letter.
No, because we plug in a number at the very beginning. So. One more. And then we're done. Just curious, what do you guys think the A sub n formula is for this guy?
N squared.
N to the third.
N to the third, yes. I know that's what you mean. So n cubed, okay? So that's the A sub n term. If I had to write the apparent nth term for that, it would be n cubed, okay? And then I'm going to say that equals, anybody know what the sum is for that one? I don't either, I'm just kidding. Actually, I do know that one. We're going to look at that one later. Later in this chapter, we'll mess with that summation formula.
Is this the hardest they're going to get?
80%.
80%.
I think that'd be fair. All right, so why don't you guys verify the first two steps for me? And then we'll work on the third one together. First step, prove it's true for 1. Make sure that it works in the first place. If it doesn't work in the first place, then like my last one didn't. Sorry about that. 202 yesterday. At 202 yesterday. You can run down there. Actually, I just leave. What time do you have to go? Do you have to go early again? Okay.
I actually have to wait for an hour for my partner.
Because the n itself is only the first term. It's how many terms I have. And so the n value is just 1 on this. Right. And you could, the thing is you can check if you're not fully believers in this, you can always do the sum for the first 2 terms, and that should be 1 cubed plus 2 cubed. And you want to make sure that that equals 2 squared, and then 2 plus 1 squared over 4. You can double check to make sure that works, right? 2 squared would be 8 plus 1 is 9. Make sure that equals 9. Okay? So you can check as many as you want. We don't need to check the first one, though. Make sure it holds true for the first one. That's the only part of the proof that we have. Okay? So, let me take this. So hopefully everybody was okay with the first one, right? 1 plus 1 is 2, 2 squared is 4, 4 times 1 is 4, 4 over 4 is 1. So it works. Okay, so we get 1 equals 1. So the first part's true. Okay, assume it's true for k. So we have s of k equals 1 cubed plus 2 cubed plus 3 cubed, and then plus dot 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 plus n cubed equals n squared, and then n plus 1 squared over 4. Oh, okay. I didn't even do the right step for that step. I know.
Over 4.
So it's k's. Okay, now I want to do that same thing I did before. I want to prove that the sum of the k terms plus the next term in that sequence, a sub k plus 1, equals the sum with k plus 1 plugged in. Okay, so that's always your third step right there, is proving that that part is true. And that's the meat and potatoes of these proofs. That's the hard part about the whole thing. Okay, so I want to take the sum of the k terms. That's this guy. This is the sum of the k terms. So I go k squared, and then I go k plus 1 squared over 4. That's the sum of the k terms. Plus I go a sub k plus 1. So I'm going to plug in a k plus 1 in for that guy right there, in for that k. So it's going to be plus k plus 1 cubed equals the sum formula, which is this guy, with k plus 1 plugged into it. So I'm going to plug k plus 1 in for all of this stuff right here. So it's going to be k plus 1 squared, and then k plus 1 squared over 4. So we got k plus 1 squared, parentheses, k plus 1 squared over 4. Okay, I show that this is true. I show that this is true, and I'll be able to run through it and make sure they're equal, and you're done. Okay? All right, so let's go ahead and do a little bit of simplifying here, see if we can't figure it out. First off, I have a k plus 2 squared here, right? Is everybody okay with that? Can I just finger math that one? Is that okay? Yeah. Like that? Okay, so that's k plus 2 squared for that one. Okay, so I'm trying to make this guy work. Well, first off, let's do a common denominator. Okay, so let's go ahead and say this is over 4 and over 4. Now, the nice part is you really don't need those over 4s anymore, right? I mean, they're all over 4, so we don't really need that part. We can multiply both sides by 4 if we really want to. The purists would say don't do that. The purists would say you can't do the same thing to both sides, right? You know, kind of like the verifying ones, they don't want you cross-multiplying, all that stuff. I don't mind if you do use both sides. It doesn't really bother me too much. As long as you get down to a true statement, I'm happy. Okay? So let's go ahead and, I think we're just going to ignore those 4s now. Now, the numerator, once again, we have a k plus 1 that we can actually factor out. This is kind of a tough factor to see, but I have k plus 1 squared here and cubed here, which means I can take out a k plus 1 squared out of both of these guys. So let's see what that looks like. If I take out a k plus 1 squared, right? If I take a k plus 1 squared out of this guy, what would be left on this one? K squared, right? So I'd have k squared for that. Plus, now here I've got a 4 sitting right there, right? But if I only take k plus 1 squared out of this guy, right? Don't I have 1 left over still? So I have another k plus 1 right there. Okay, I took a k plus, let me show it to you this way. If I took k plus 1 cubed, and I divided it by k plus 1 squared, right? What would that simplify down to? K plus 1, which is that guy on the inside right there. Since I have 3 of them right here, and only took 2 of them out, right? I factored 2 of them out, I still have 1 left over right there. Okay? What about the other parenthesis? Which one? That was the common factor from this and this. I took a k plus 1 squared out of both of those guys, right?
Okay.
I'm doing a grouping factoring, right? It's factoring by grouping, okay? It's kind of a tougher grouping to see, okay? Now I just simplify. Now once again, I have that over 4 stuff, right? I'm just going to leave it alone. So k plus 1 squared, and then k plus 2 squared, right? Now I'm just going to try to show that this is good to each other. Notice we also have a k plus 1 squared on both sides right here, right? So I'm really just trying to show that this guy, the inside here, equals k plus 2 squared, right? So I'm just going to work on this inside real quick. Well, that's k squared plus 4k plus 4, which I can factor. K plus 2, right? K plus 2, or k plus 2 squared. Done. Jackpot. Yeah, we did 3 problems.
Is that K plus 1?
That's a good one.